It's always hard to guess with computers, and we're a little bit spoiled by Moore's law from the 50s and 60s, just taking us from these really simple devices to what we have nowadays. We do not want to make the same mistake we made with, for instance, nuclear fission and fusion, where we got the development in 20 years and just assume the next one will get to us in another 20. Quantum computing might be many decades before we see any real major progress, but at the moment, we have made quite a few major leaps and actually are doing some real calculations with this. We have a whole bunch of problems in terms of making it better, though. And the biggest one is the actually getting the right answer out of it. As an example, if we were using the random source before, let's say I locked somebody inside a quantum box with a phone book, and I told them, I want you to find a phone number. And if you call this correct phone number, and here's the phone number in this book, someone's going to come by and let you out of this box. That person is then given a random number generator. We shut the box and they search. A whole bunch of different quantum ghosts of them appear, searching various pages, but the one who finds the right one calls that, and the person comes and opens the door. And that's one example of a data extraction, though that would never work in actual reality because quantum doesn't do well at the macroscopic scale. But you can get errors from things like that. For instance, imagine one of these quantum people searching that page didn't call the right number, but instead accidentally called a pizza delivery place that showed up and opened the door to deliver the pizza. Now we have a wrong answer. And we have things like this happen with quantum computing, where we have error in terms of the data. We used to have this with normal computing too, but we solved it fairly early on. This is probably going to be a lot harder to do, and in many ways it's the hardest part other than actually keeping all of these particles entangled. It's not just trying to keep one particle like this. We have to keep several thousand, potentially, or millions, all entangled with each other simultaneously. And this also requires them to be at just a hair above absolute zero, temperature-wise. And then, of course, we have our third problem that has to be overcome, which is the software. All of this runs on algorithms being handled on classic computers fed into these things. And those algorithms are an area that we still have to do a lot of work on to improve them because we're not quite using the original pure algorithms like Shor's, but ones we've had to adapt along the way. So those kind of three areas, the software and the hardware areas, are the ones that are going to really control limitations on advancing. How much bigger can we make the entangled system? How well can we actually pull the right answer? And how do we actually get the right algorithms to ask the right question as well? Well, we tend to think, with the modern phone and the laptop, that this would be something you have, at your home, that you would have a quantum computer. But in fact, you probably never actually have a quantum computer in someone's house. They have to be run at such very low temperatures, and they have to be, even though they are very small devices in terms of the entanglement, there's so much associated equipment that isn't likely to get too miniaturized. So most likely, you would always have classic computers that people access it through on the cloud, and you just buy time or get time on a quantum computer that you were linked up to. And the thing that would be most likely for an individual person to use would probably be something with encryption. But for stuff that we would actually get to see on our computers, would probably be stuff like weather forecasting, for instance. It has a lot of options to allow us to do way better weather forecasting than we do now. And there are a lot of other examples, in terms of the science, there are great things. It might finally let us model how life started, abiogenesis in the deep oceans, which is one of those examples where our models can't really be, we have approximation algorithms that we use to cover these really huge numbers, but they don't really seem to be up to snuff for covering things like those chemical interactions in the early deep oceans. And then those same algorithms, ironically enough, would be the kind of things we'd use for dating services in terms of finding the most optimal match for a person based on not just a simplified number of traits. We have to simplify traits normally. Here you could actually have 1,000 different traits with 1,000 different subtypes, and a quantum computer could actually match up and optimize all of those. And then, of course, there's the possibility of using election modeling